In the previous discussions, we have seen how this moment area method can be used effectively to find out the slopes and deflections of certain simple beams, simply supported beams as well as cantilever. Now, we are required to see some more results like the fixed moments of certain spans of beams whenever we analyze frames, rigid jointed frames as well as continuous beams using any indeterminate structural analysis like flexibility method or stiffness method. So here we have a one span fixed beam, both ends fixed beam with properties E, I and L subjected to UDL throughout. Reflected shape of the beam would be like that. Slope is equal to 0 here, reflection is equal to 0 there, and similarly slope and deflection are 0 at this end also. Now let this be the fixed moment due to W per meter, due to fixity over here. Define that as MA. Let this be the fixity moment at this end. Define that as MB. So these are the reaction moments due to W per meter. Fine. If I split the bending moment diagram of this into three parts, like the simply supported bending moment diagram for UDL in a simply supported beam, considering these two supports are simple supports, will be the bending moment diagram. The BMD for MA would look like this. Sagging bending moment diagram. This also is sagging bending moment diagram. The BMD for MB would look like a right angle triangle but with negative ordinance because MB is going to sag the beam. We assume initially that the moments, fixed moments at end A and end B are clockwise in nature, so that this moment is going to sag the beam and this moment is going to hog the beam. So when you sum up these three diagrams, we are going to get the final bending moment diagram, BMD. And now the conditions available here and here at these two supports are slope at this end is equal to 0 and slope at this end is equal to 0 if we exploit that. So theta A is equal to, as given by the moment area method, will be equal to, for this diagram it is W L cube divided by 24 EI as derived earlier. For a sagging moment MA at this end, the rotation here will be equal to clockwise rotation, so plus sign, plus MA L divided by 3 EI, and because of the hogging moment at the other end, the rotation at this end would be equal to minus, rotation is anti-clockwise, so minus sign MB into L divided by 6 EI. And according to the method of consistent deformation, this rotation should be equal to 0 over here. So the algebraic equation in terms of MA and MB would be MA, say 2 MA minus MB is equal to, we multiply throughout by 6 Ci divided by L, we are going to get minus WL cube by 24 EI into 6 Ci divided by L, that becomes minus WL square divided by equation number 1. Similarly, the condition at this support is slope here is equal to 0. If we exploit that, the rotation here due to this bending moment diagram or this loading would be anti-clockwise minus W L cube divided by 24 EI. The rotation here due to this load alone, MA alone, would be anti-clockwise. So minus MA into L divided by 6 EI as derived earlier, and the rotation here due to the moment MB using this bending moment diagram would be clockwise. So plus sign MB L divided by 3 EI. Sum of these three quantities should be equal to 0 as per this diagram and the method of consistent deformation. So the algebraic equation in terms of MA and MB now would be MA minus sign plus 2MB is equal to WL square divided by 4. Equation number 2. If we solve equation number 1 and 2, like say equation number 1 plus 2 times equation number 2, 2MA minus 2MA will cancel, minus MB plus 4 times MB would be 3MB. Is equal to minus WL square by 4 plus 2 times WL square by 4 would be WL square by 4. So MB is equal to WL square by 12. Equation number 2 will give us MA. MA will be equal to WL square by 4 right hand side minus MA here is equal to minus WL square by 4 minus 2 times WL square by 12. When you simplify that, we are going to get MA is equal to minus WL square by 12. So the fixed moment at the left end due to a UDL in a fixed beam would be anti-clockwise WL square by 12, and on right side, right support, it is equal to clockwise WL square by 12. Further, if you have an eccentric point load like this, say of magnitude W, this distance is equal to A, this is equal to B, A plus B is equal to L, this end is capital A, this end is capital B. The BMD would look like this. This is for the simply supported span and W alone. W into A into B divided by L will be the maximum coordinate. There is a moment MA due to fixity. There is a moment due to MB due to fixity. The BMD due to MA would look like as before. The BMD due to MB would be like this. And the equation of compatibility from the method of consistent deformation would look like the slope here actual slope here is equal to 0. So slope here is given by the slope due to this one that is given in the previous discussion. This is W A B into 2L minus A divided by 6EIL plus slope due to MA L divided by 3EI, slope due to MB minus MB L divided by 6EI, slope at this end due to MB is minus MB L divided by 6EI. Minus sign is because the slope is anti-clockwise, and plus sign is because these two slopes are clockwise. Now we can form an algebraic equation from this. The second equation, this is equal to, of course, that is equal to 0 as given by the compatibility condition, and further theta B would be given by the slope at the other end due to this loading or this bending moment diagram in a simply supported beam, that is W A into L square minus A square divided by 6EIL of course. This slope is anti-clockwise. This slope is also going to be anti-clockwise because of MA at the end B. So MA into L divided by 6EI and MB into L divided by 3EI. That also is equal to 0. If we solve for these two equations, we are going to get MA is equal to W A B square divided by L square, and MB is equal to, of course, MA is having a minus sign. MB is equal to plus W B A square divided by L square. And remember, we have A is equal to the distance between end A and this load, and B is equal to that between the load and the other end B. So these are the fixed moments. We have an anti-clockwise moment equal to W A B square by L square at the left end, and clockwise moment is equal to W B A square by L square at the right end.